All right. Well, thank you again, everybody, for joining us. We thank you for definitely those who are joining us a second time. The last time we went through the overview of all of the KBC networks transmission and power solutions and the product overview, essentially. And in this one, we're going to take a deeper look at the wireless and remote power technology. Now, we have had a few questions come back to us as to definitions of the terminology, so address that real fast. What do we mean by remote power? And of course, wireless transmission is pretty obvious. We're talking about having a remote location where we need to bridge a gap where there's no cabling, a long distance application, and we have a bridge wireless system that's in place. And so the remote power refers to the power that's available or not available over on the side where the devices that you need to connect back. And so we're talking about maybe you have high voltage AC and you need PoE power. And so having a product that does that conversion, the transformer that takes the AC power and gives you PoE or PoE plus or PoE plus plus high power, that sort of thing. So talking about remote power technology solutions that provide the type of power you need based on the type of power that you have. So if that power is there constantly, then there's a solution that deals with that. If there's power that's there inconsistent because it drops out, then there's a solution that goes with that. And of course, if it's off grid and there's no power, then a solution like solar power that is giving you constant power via battery backup. And so we'll talk about those things as we go through, giving you an idea of how to choose the right product and create a design that's going to be appropriate for your application. I do want to say from the outset that a lot of what you're going to hear, the majority of it is based on the technology and the physics and all of that, of course, but a lot of it comes from what we have learned as experts in the field, but based on dealing with support and just kind of learning on the fly. And so when we're talking about power, we're not specifically electrical engineers or anything like that. When we're talking about batteries, for example, we are not battery salespeople. So if there's something you see on that particular slide that you may have heard something differently, then yeah, definitely do some more background research on those type of batteries and glean that from what's available online. We're giving you the basics so that you can understand what it is that we think through when you come to us with an application asking us to do a design. We want you to be able to continue to come to us for application design, and that's what we're here for. We're here to continue to work on those for you. If you come away with this being able to take a stab at it yourself, then fantastic. Then we did a good job, I guess. But we want you to be able definitely to continue to come to us, and we have the pre-sales and the post-sales support features we talked about in the last session that are there for you as well, and they will continue to be. So we want to teach you how to design the wireless video system, but still be able to rely on us as well, because that's what we're here for. To be able to select the most cost-effective products and creating a robust network, because there's a lot of features that are available in cameras and in intercoms and in all the different types of solutions that we are needing to get across the wireless connection. And so building that network is important to have a solution that's able to support it. To provide to identify, the appropriate power solutions for an end-to-end connectivity application. We talked about remote power just a second ago, so we'll dive deep into that in a moment. And knowing that you have all of that available in these products to have not just the connectivity, but the power end as well. And give you some tips to avoid those misunderstandings and possible installation errors and things like that to be able to make sure that when you put all of this in, when your techs are out in the field, they're able to do it easy because it's a simple installation and you've understood what things to avoid. So when we get into wireless transmission, we're going to talk about radio frequency theory, talking about the FCC, what they allow, and what is a license-free product versus what would be something that you would have to get a site license from FCC for. We talked a lot about line of sight in the last one, and we're going to deal with that again. Fresnel zones, what that means, and also how the antennas work, the propagation of them. If you were able to see physically what they look like as the radiation is coming from the antenna. So we'll show you that. Wireless topologies like point-to-point, point-to-multi-point, and mesh, and when to use each different type. And what to look out for as far as interference, third-party RF interference. And with remote power, SPBs, that refers to security power box essentially. So it's an enclosure with a power supply and a switch and other devices that are in there to provide the type of power that you need. That's when there's a constant power available. When there's not constant power, you have switched power providing the PoE or HPoE or whatever it is that you need in that application, and then the solar solution as well. So the frequencies and kind of what they look like and how it's measured and just the theory behind all of this. If you were to see the wavelength, it would look very similar to what you see on there, the squiggly lines. Wavelength just is the peak to peak and how far apart they are. And the further they are apart, the slower that it is. So the shorter that they are, the faster they are. And that speed is measured in hertz. So way back when you may have had a cordless phone that operated on 900 megahertz. 900 megahertz was a slower speed, so the wavelength was longer. 2.4, that's little shorter wavelength, so a little faster speed. And in a moment, I'll show you a slide what these things can do, the frequencies that is. And then 5 gigahertz being kind of where we're at right now, and yet there are other frequencies that are available that are faster, that can carry more, and which will allow for lesser interference, and I'll talk about that in a moment as well. So back in the day when you may have had a 900 or 915 or 900 megahertz phone, the frequency was real long and looping and slow. And so it had ability to penetrate a great deal. You can go really long distances with it. So naturally it was the first frequencies to be used for what was being carried. So a cordless phone, which we don't use anymore, of course, only had to carry voice. It didn't have to do a whole lot. The video signals, the video systems in the day weren't like what we have now, so not a whole lot needed to go over those frequencies. And so you can get through a lot of trees and you can go long distances and things like that. Of course, that frequency became very crowded. It moved on to 2.4. If you had a 2.4 phone, same thing. Of course, 2.4, very popular for just the home use, commercial grade access points for Wi-Fi. So 2.4 still had that ability to penetrate through walls and in outdoor trees, things like that as well. It was affected a little bit more by water, and so if there's water collection on leaves and the trees or over a lake or whatever, there was a lot more adverse activity there that had to do with the 2.4 signal. And then the 5.8 gigahertz frequency, which had the most ability to carry video signals, and so that's why we use that. And also when it says 5.8 gigahertz, we're also referring to the lower channels, which are actually 5.1 and 5.2, so really all of 5 gigahertz. And we will be opening, we've heard now that there's 6 gigahertz, so FCC has opened that. So what does that mean as far as the FCC opening different frequencies? Well, with the license-free frequencies that we are able to use in our industry, and also with the devices that you're familiar with, your access points in your house or in your business, and those type of devices, they all operate on frequencies that FCC has set aside and said, look, you can use all these channels, no problem, but there's limitations. And so the limitations have to do with how much power is able to come off of the radio, out of the antenna, which deals with, of course, how far you can transmit, things like that. And also, because it's license free, I can deploy a license free product, and so can my neighbor, and so can his neighbor, and so can anybody. So as these devices are put out there, anybody can use them. But what happens is, if I'm going to use a license-free product as a user, and I take my license-free product on any of these frequencies or any other frequency that's license-free, and I apply power to it and I start transmitting from it, basically what I'm doing is I'm entering into a non-verbal, non-written, essentially, agreement with the FCC that says that I am using this device to the standard by which they've allowed me to use it. So I'm taking a judgment, leap of faith, whatever it might be, that says that I understand or I believe that this product is built to the FCC limit and no more. And so the products that you use have a little label on them that basically tells you what it's able to do. And one of those things is that it has to accept all forms of interference that may come from other devices that are using these same frequencies. And if there is, then you have to change frequencies, or you have to align differently, try to get away from what's interfering with you. You can't try to overpower them in some way. So you have to stay within the legal parameters. And so, of course, KBC, we make all of our wireless products to that standard, and we make sure that it's a legal product that we put in the field. So we have standardized on the 5 gigahertz, and as FCC opens up 6 gigahertz, we just heard in April that that's what's going to happen, then we'll be looking to open up channels within that frequency band as well. Naturally, as it went from 900 megahertz to 2.4 gigahertz to 5 gigahertz into 6 gigahertz, and there's even ones that are much further, much higher frequencies that can be used. They're much greater cost and also really difficult to align, but they are available as well. But naturally, as that progression took place, more and more devices went from the ones that were crowded to the next one, and everything crowds. But with 6 gigahertz, there's going to be a lot more frequencies to choose from. From what I understand, and I don't know how many frequencies will be available to us, but we're told that there's 1,200 megahertz worth of frequencies. Right now, when we're using the 5 gigahertz, we have less than 1,000. Much less than 1,000 to figure that one out. But there's the 6 gigahertz will give us a lot more frequency ability. Now that's all license free. So any other product that does not use these frequencies would then be considered a licensed product. A licensed product would mean that it operates on different frequencies. An example of this would be a 4.9 gigahertz device, and that's been licensed for public safety use only, for fire, for first responders, things like that. So if you qualify, or if your end user qualifies, then you could use a 4.9 device. We used to offer a 4.9 device, but we no longer do. There's not very many frequencies on it, and so we did not find the success that we thought we would have with that, but those frequencies are definitely available, and they are licensed only for public safety. Now, there are other frequencies as well, more in the 2.4 range, and probably others that I'm not aware of. But at any rate, other than the public safety one, you would have to go through FCC and fill out documentations, give them an understanding of what you're doing, and I'm sure a cost that goes along with it. So a lot of things that would go along with a licensed product, but you would be able to do a lot of power on it, and you would be free from interference with those products. But these products are all ability to not have to do any of that. So that's the advantage of it. So to show you some of the frequencies, and my slide is a little limited, so the orange ones only show 5, but just understand there's actually 9 there. But dealing with the top part first, the 2.4 gigahertz. 2.4, like I said, way back in the day, the 2.4 cordless phones, but more these days with 802.11b or G or 802.11 BGN. The way those frequencies would work, if you take a look at the right, you have the 3 blue half circles, if you will. Those represent the different frequencies that will not overlap with each other. So you could use 3 different systems, and you can set them on 3 different channels, and you wouldn't interfere with yourself. But there are a whole bunch of other channels that are available that all overlap. So that's one reason, as also a lot of interference and some other reasons that we do not use 2.4 in our systems. It's just a crowded and a lot of different bleed over, not very many frequencies. And also kind of the last slide, you can do more with 5 gigahertz. You just need to have more line of sight. Whereas with 5 gigahertz, you can call it 5.8, 5 gigahertz, whatever. There are 4 5.1, 5.2 frequencies, and there's 5, 5.7, 5.8 gigahertz frequencies. Every channel is 20 megahertz wide. So what that means, looking at the megahertz now, megahertz and gigahertz, is just saying it different ways. 5745 to 5765, that center frequency or the carrier frequency is 20 megahertz difference between each other. So 5745, 5765, 5785, and the same holds true for the 5.1, 5.2. It starts on 5180, 5200, 5220, so the 20 megahertz wide. So that's what the different channels are. Now we could take these different channels and we can bond them together and create larger frequencies. So that there's a 40 megahertz wide option. It gives you less channels, but it gives you a larger frequency grouping, a bonded channel, to be able to do more throughput on it. So now if you see that 5825 one, it kind of stands alone. So 5825 remains a channel that's still available in the 20 megahertz spectrum width, so that you can bond and get more throughput for the lower frequencies and then still have that 5825. Also, 5825 is an interesting one because it does not come onto channel scans, because those are designed to look for access points that are on 802.11a or N, or even AC, and I'll show you what AC is here in a second. And so 5825 is not used as an access point channel for typical Wi-Fi, but we have it available as a frequency to be used as well, to do video or to do access control or to do intercom or to do whatever it is that you want to send across it. So there's less frequencies when you bond them together than when you have them in the 20 megahertz wide. Here is an 80 megahertz wide. So this takes the entire 5.7, 5.8 and gives you a large frequency. And then you can do the same with the 5.1 and 5.2 channels as well. So just a way to incorporate all the frequencies together to get more throughput. And we do this particular one, the 80 megahertz wide channel, with our high throughput system, the West 3 HTG. So going back to the frequencies and kind of what they look like, that squiggly pattern we saw before, it's expanding out like a football shape pattern. So it starts small, it continues to widen and grow, and then goes back down again as it's being pushed out from the transmitter. And so that's why that Fresnel zone, that zone that we need for clearance, a wide open area, needs to be wide open. because it's expanding out in all directions. It's not 2D, it's 3D. So not only are we talking about the lower half, because the upper half of the Fresnel zone is usually airspace, the lower half is what we're thinking about in terms of devices that we need to stay above so that they don't obstruct our Fresnel zone, but also left and right. So we use a bus as an example. If you could take something the size of a bus, like a school bus, if it were able to fly from where you have the camera, the client, as you see there in that picture, all the way to where the host is, the control room, the NVR, whatever you want to call that. And you can imagine that bus going across that clearance and not being obstructed by anything, then certainly you have clear, wide open line of sight. Now, at a short distance, as you can see in the table, you don't need that much. It's more like 5 feet. But having that bus-sized zone is a good rule of thumb, especially as you get into further distances. So the further you go, the more clearance you're going to need. There are other antennas, and how they send out their radiation patterns is a little different than what we've been talking about with the directional. You see that dish there. There are omnidirectional antennas, and there are other types of directional antennas. We use what's called a patch antenna. So it doesn't look like the dish that you see there, but still has much of the same capabilities as a dish. It's easier to work with. It's better for aesthetics, and the antennas are integrated and things like that. But let's take a second and look at the omnidirectional antenna and what it looks like. So it looks like a donut, essentially, because again, it's 3D, it's expanding out, but an omni is going in all directions, 360 degrees, but it has certain capabilities as far as elevation is concerned. So that's where a higher gain antenna, higher gain just means that we're taking that signal and we're kind of flattening it out. As you can see on the directional antenna example, that signal is being flattened out by a higher gain antenna, just a larger antenna. So as far as omni, and I tried to color code this to keep it separate so you can understand, there might be a 3 dBi omni antenna that would look similar to that donut picture in the white box there. But then if you want a higher gain antenna, you have to flatten that donut in order to go further out. So if you go to a 13, then that continues to flatten out even more so that it's less and less like a donut, but it's all going around in a 360 degree. Whereas with a directional antenna, the radiation is being sent from the antenna out in a direction, and so it's being flattened in a different way. So I tried to use 3 dBi the same as omni and directional and put them in blue. We actually don't have a 3 dBi antenna, but just to kind of make that similar. We do have a 5 dBi omni, but we don't have a 5 dBi directional. We have a 9 dBi directional. That's kind of our lowest gain directional antenna. And then our standard directional antenna is the 17 dBi, whereas with an omni, we have a 13 dBi. So that's why it's a little different based on the examples given there and the color codes. And I did that because we move on to this slide here to try to show why we use different antennas for different reasons. An omni would make sense being able to just put an antenna out there, a radio out there on a pole, wherever it might be, and then throw up another pole and put another one up, and so on and so forth. But there's limitations. The first limitation is range. Omni antennas don't go as far as a directional one does. So if you have two small omnidirectional antennas, you can get out of range very quickly. And so you would need to use a higher gain omni in order to make up that difference for the range. Now, what is the range? Based on 5 dBi to 5 dBi, or 13 to 13, or even 5 to 13. And the same goes for the directional. And the answer, because it's a common one, how far is it that your antennas can go? The answer isn't as simple. The answer is we can tell you what we've tested and what we're comfortable with. But there are too many variables in every single environment to be able to say that if you had a 5 dBi Omni and you took another 5 dBi Omni, then you should be able to get X number of feet. Omnis, again, they don't go as far. Also, there's an elevation thing or an alignment limitation with Omnis, as you see with the two purples there. They're not able to be aligned. So if you're on different elevations, it's very hard to really line those up and get a real strong signal. Whereas with a directional, you're able to aim them up and down, left and right, and to be able to really lock them in. So we can tell you what we feel comfortable with. For instance, we deal with directionals much more than omnis, so that's why I'm going to give this to you in directional as compared to the omni. But the directionals, if you had two of our highest gain directionals, the 17s, and you had wide open line of sight and you're up high on both ends, it's been tested at 5 miles. We've had people tell us success stories even further than that. I will say that when we're talking about all of these different limitations, whether it be line of sight or interference or even angling and alignment and how it all looks in terms of the signal based on degrees of reception, things like that, like the picture on the bottom right where there's a lower gain receiver and two higher gain antennas. So all the different things that we're talking about and we're telling you it can do X. We have heard so much from the field where it doesn't shock us anymore to hear that, well, you said you need clear line of sight, but I shot through some trees. Or you said I had to be within 60 degrees of my receive point, but I was a good 100 degrees and it locked in just fine. And the reality is that every environment is different, and every environment, or I should say, some environments are much more forgiving than others. And so there's times where we say you got to have a clear line of sight and you power through things. The antennas are built to go long distances. I just mentioned that the directional ones, the highest gain directional ones, are able to do 5 miles per our test. And we had someone do 8 miles. So things like that we would never say go for it, but we have heard so many things come back to us saying worked out great. So with the directional, let's go to this. Okay. The different types that we have, as I mentioned this a moment ago, we do have the omnidirectional antennas. We use them for when both sides are in movement. So for example, maybe a crane application, or maybe our mobile surveillance units would have one of these on there. Something where it needs to be deployed for a certain amount of time in one place and then moved over somewhere else. An omnidirectional antenna would make sense. An omnidirectional antenna would also make sense if you have one receive location and you have multiple transmit locations around it in a 180 or greater type angle. It would make sense. However, we've seen stronger signals and more success when we use directional antennas in those cases. And so we offer them because, like I said, the crane application or the mobile application, things like that. And we do have upgrade antennas for the Omni to overcome certain obstacles as well. Our directional standard units are 9 dBi and 17 dBi in both our standard throughput and our high throughput systems. So we can use a 9 dBi as a receiver and really open up that angle to have more transmitters in the field coming back to it. And so the antenna is right behind the white cover in both of those. So you would aim the face of it and not the end of it. So here we go. Believe it or not, people have tried to align our antennas kind of like a shotgun. That's not the way to align it. The antenna is behind that white face, so you're facing it outward. It also gives you the ability to align up or down, left and right. And the mounting equipment that comes with it makes that pretty obvious as well. Alignment is not applicable on an Omni, so you mount it up there, the Omni antenna sticks straight up, and that's what you do with those. But with the directional, alignment, especially if you're going further distances, can become more critical. Let's say you have an application where you need to go, let's just say a mile. You have wide open line of sight, you need to transmit a mile, and you have these 17 dBi antennas. A good field use would be that you would eyeball it to start with on both ends. There's LEDs on the back to help you with alignment too. So you would look at the LEDs, make sure that you've got all 6 LEDs that are on there, and make sure that your antenna is mounted so that the Ethernet port that the cable comes in, that's at the bottom. You want that facing down. And again, the mounting makes that obvious. But you would start with one direction that you would move it, either left or right. And there's an interface, a web browser. You would just go in and take a look, and there's a signal strength indicator there. And so basically, you would just go incrementally until, and in the same direction, until that signal starts to go down. So as it's increasing, you keep going the direction you're going, of course, and then once you lock it into a left-right position, you would do the same thing with up and down, or vice versa, of course. So that's just simple alignment on these antennas. Wireless topologies, point-to-point, means that you have one single remote point coming back to one single receiver. The most easy application to align because they're both on each other. Point-to-multipoint, where you have multiple remote locations, and it doesn't have to be 2, it could be 3, 4, whatever, coming back to one common receiver point. So that one common receiver point would need to have clear line of sight to all of its mates and be within the degrees of reception. So going back a few slides, the 9 dBi would give you 60, 65 degrees of field of view, whereas a 17 dBi is much smaller. It would be more like 30 degrees or so. So you want those to be more in line. But you can still do that with a point-to-multipoint setup. And then mesh. Mesh is a common buzzword, and so people say I need a mesh system. They're usually talking about needing to go from point A to B to C to D and so on and so forth because of line of sight obstructions. It also means that they can all talk with one another. So in this example, A is not only going to B, but it's also talking to D and E directly. And then it's using the center point D to get to everything else. And so the common misunderstanding, if you will, is that you can just take a mesh system and deploy all the units and just turn them on and let them go. But the problem is with video, it's not a good idea because it wants to find its best path to where it is that it's being pulled back to, the final receive point. And so while that gives you a lot of options in case there's reasons why maybe from point A, let's say G is our head end in this case, maybe D goes down for some reason, so you have all those different points to get back. It's not like the system knows when it ought to use a different path, unless there's a power failure or something like that, then that would be obvious. But people expect that if there's interference, then the radio would just say, okay, I'm going to go back via one of my other pathways. But the system, as long as it continues to have some kind of connection to the mate it's locked onto, it's not going to do anything. And so I think that's the misunderstanding with mesh, that it's not going to necessarily do what you're expecting it to do, because it's just not that smart. And then if it was, then you might have radios dropping all the time anyway, because it's finding new paths all the time. So it becomes very complicated. It's very complex. They are also very difficult to deploy because you need to route them properly. Again, you can't just put these up so that all of them are out there talking with each other. It just doesn't work that way. So here are the benefits, and I kind of mentioned a few already talking a moment ago. Point-to-point is simple, it's the easiest. it's not necessarily the most cost effective when you get into a larger system, because you don't want to have a whole bunch of receivers on your main building, assuming you have line of sight back from every location. So you would want to move to a point to multi-point system in that case. Multi-point has that one common receiver. We talked about that. And the receive antenna needs to be within that appropriate beam width to connect to each transmitter. So I mentioned that already. And mesh is complex and costly, but it is for critical uptime applications. And on line of sight requirements, you're repeating the signal a lot. So some things to think about as far as which topology you want to go with. And most of our designs wind up being a blend of point-to-point and point-to-multipoint, with the final consideration being that all of the video gets back via the most cost-effective solution and also the easiest to deploy. Okay. Come on. There we go. Okay. So interference, we kind of already covered this, so I'm just going to move through it pretty quick. 2.4 Wi-Fi signals can interfere. Bluetooth operates on 2.4, so that's something that can interfere. 5 gigahertz has much of the same type of wireless Wi-Fi technology that's out there, and also ground-to-air radar would affect the lower frequencies, and so that was one reason why the 5.1, 5.2 frequencies were available way early on, and then they restricted them, FCC did, and then they reopened them again several years ago. So that's been back available to us for quite some time now. And so channel selection is more successful on 5 gigahertz frequencies, and antenna alignment is easier with 5 gigahertz and the directional antennas. We talked about that before. And so I'm going to kind of move through this to get to remote power. So remote power, the constant power, when that's available, we have our security power boxes, the SPBs, and we have a lot of different options to go along with that. But if your pole has switched power and you need to have a battery backup to be able to provide power during the day, we have a solution that does that too. And then we'll talk about solar. I want to save as much time for this as I can. So here's all the different types of models of wireless antenna and which model of the SPB would be used. We can get this out to you later on because there's just way too many model numbers and things to talk about here. But the point being is there's different power input on the standard West 3 kit and the radio that's used in that West 3 kit, which is the West 3 AXCA. And that A at the end of that model happens to mean that it has a 24 volt DC PoE input requirement. So the SPB injector needs to have a passive 24 volt PoE output in order to power it. But we have a 48 volt PoE device, which is the West 3 AXCF, and you get 2 of those in a West 3 KT PoE. So for that radio and that kit, you would use the SPB models that end in -48. And it also can power by a PoE switch too, the radios that come in that one. And the HTG, the high throughput, even though it ends in CA, much like the first one, that's 24 volt, this one is actually PoE powered. So you would power it by the same type of SPB box that ends in -48, just like the West 3 KT PoE does. And the HTG also can power by a PoE switch. So the SPB 4AF48, which has a PoE switch in it, can power that high throughput radio. We also make a SPB that has a hardened PoE switch plus a high PoE output for a PTZ or something that's going to require in excess of 35 watts. And we have a PoE Plus device that can power up to 35 watts too. So we blend all these together and we create different solutions for different needs. And this is just an idea to show which radio would get which SPB. If you're doing a relay, then you would have to match up the the outputs of the SPB based on the wireless input and make sure that it works. So let's take a look at that real quick. So here's just the example of the different types of cameras and wireless antennas. And these SPB boxes can power other things too, not just cameras. They can power intercoms. They can anything that's PoE powered, we can power with this as well. And then, as I mentioned, a relay. I'm going to show you that. So here's a relay application. So this pole on the far left has no line of sight back to the very end receive location. And so we need to hit the pole in between, but we're getting cameras there as well. So there we would need a switch in order to power multiple devices. And so you would want to use the PoE radios because you have that switch at the middle point. So that switch at the middle point is going to need to power your cameras that are on the pole, but also one of the wireless antennas too, because there's only one antenna output that's going to power the radio. So when you have more than one radio, the switch needs to power one of them. That means that you lose a port for your cameras. So in this application, we show 2 cameras. You really could do as many as 3. And we do have capability to do more. It would be a different box with a larger switch in it, but we can do that too. All right, so moving into the UPS discussion and solar discussion that's going to utilize batteries and how we take all of the power requirements and put them into the terms that we need in order to provide the battery backup and also the solar kit that's going to be able to support it. So it's all the same calculation, whether we're talking about trying to determine watts or we're trying to determine amps. Watts is simply amps times volts, and then amps is the reverse, so it's watts divided by volts. This slide tells us that 12 watts would equal 1 amp at 12 volts DC, or half an amp at 24 volts DC. And then 48 volts, 12 watts would be a quarter of an amp. And then talking about stored energy, we usually talk about amperage with stored energy. So we talk about solar kits and UPS kits, we talk about watts, but then we have to talk about amps when we're dealing with the batteries, and I'll tell you why in a moment here. So these are the calculations. Basically, kind of jump ahead a little bit. When talking about batteries, a 100 amp hour battery, basically that means that it can support 1 amp of constant draw for 100 hours, or at least 1 amp of draw. After 100 hours, it will die. Now there are a couple different types of batteries. There's the sealed lead type, and then there's lithium type, and those have different discharge rates. The sealed lead acid batteries, generally you divide them in half, because at 50% discharge, it effectively goes into low voltage disconnect for the sake of the battery, so that you don't damage the battery. Whereas a lithium battery, you can do so much more. You can do nearly 90% on a lithium. And so that's important in a moment. So discussing battery backup for a UPS. So we have a pole, gives us power at nighttime. We're going to trickle charge batteries. And then in the daytime, we're going to run off that battery bank in order to be able to provide power during the day. Now, keep in mind as we talk about this, also with solar, that there's no AC outlet that's always energized 24/7. In this solution, there is AC power, but it's only available at nighttime. So we want to avoid putting in devices that take the DC output from the batteries and give you AC power so that you can plug in a power supply. The reason we want to avoid that is because you go from an AC input to a DC battery bank to an AC output so that you can plug something in, and then your power supply is also providing DC to your equipment. And so you have this AC to DC just back and forth, and that creates power inefficiency. And it's important, especially with a battery backup system, that you keep the power as efficient as possible. So when we build these systems, or when we build your spec and your design, we are trying very hard to avoid the need to go back and forth from AC to DC. And the way you would go from AC to DC back to AC is with an inverter to give you an outlet. We have those available, but again, we try to avoid them. We want to use DC at all times. With the battery bank, if you have two batteries, you can wire them in parallel to get 12 volts and greater amperage, or you can wire them in series to get 24 volts and keep the same amount of amperage. It's all the same calculation, just depending on whether you're dealing with 12 volts, 24 volts, 48 volts, and so on. You can do all these different voltages with the batteries. Usually batteries are 12 volts, so we try to use as few batteries as possible. We have found that 24 volts on the battery bank is the most effective in terms of providing power to the system and the controllers and the chargers and things that are all in there. So this system would take the battery charger from the AC input from at nighttime when the power is there, charge the battery, and then give you either 12, 24, 48, depending on the model number. And that model number tells you how the batteries would need to be wired. So if you're using a UAL2-12, for example, that unit can fit two 100 amp hour batteries, and you would need to wire them in parallel. But if you're using a UAL2-24, takes the same number of batteries, but you got to wire them in series. Also, if you have 277 volts or higher, it needs to be stepped down. So it's got to be within that voltage range. Solar. One thing that we get a lot of is, I see that your model number has a 100 watt indicator at the end, but you're telling me that I'm in zone 3 and I'm only getting 14.5 watts of power. How does that? Well, what that means is it takes the amount of power during the peak hours, the peak sunlight hours in your zone in the middle of the winter on the shortest day of the year, December 21st. And the calculation is done so it takes those number of hours multiplied by the wattage input from the panels and divided then over 24 hours. And that gives you the 14.5. And actually, 14.5 would be the amount of power total that you can use. But because we need to run all that equipment at nighttime when there's no sun, we can't just say you can run 14.5 watts on a 100 watt panel, because you would need to be able to provide power in some way at nighttime. The sun's not shining. So that's when we have the battery bank. We take all of that power and we store it in the battery bank. But we need to make sure that there's power available at night. So we are only going to use half the power that's available during the time that the sun is out. That way we can reserve the other half of the power at nighttime when there is no sun. So that's where we arrive to actually being 7.25 watts, because 14.5 divided by 2 is 7.25 watts. So that's what the effective 24/7 power would be available in zone 3 on December 21st. Now a 200 watt kit, you get two 100 watt panels, so you would multiply all that by 2. Same goes for a 300, you multiply by 3, 400, and so on. So let us do all these calculations for you, but this is just an idea of why we come to the amount that we arrive at. You can wire the panels in a dual panel system in series. It gets you 24 volts, and the battery bank, wire those in series, would also give you 24 volts. This is a common mistake with the dual panels that mount on a pole and they're separated. When you mount them on a pole, you want to make sure, of course, you want to make sure that your solar panels are always facing south, and you want to have them separated such that they don't shade one another. So if you look carefully, you can see just a little bit of shading on there. The amount of power loss just by that little shade amount alone is pretty drastic. And so you want to make sure that it's completely clear of the other. Our 200 watt panel kit, those two panels are actually side by side, or they're connected to each other essentially, so you don't have this. But as you get into the larger kits, this one I believe might be a 600 watt kit, so each are 300 watt panels. Those you can't have right next to each other, so they need to go on the pole with some separation. Also, even larger than that would be a 750 watt kit, which is two 350 watt panels. And those two, of course, would need to be even more separation because they would use two 350s, which are even a little bit larger than a 600 that uses two 300s. So just something to look out for on that. Here's the battery discussion, which kind of already covered. This is how we arrive at how much stored power it is that you're going to have, both on a UPS and also a solar power system. Why it is that you would need to have more power or more batteries available on a sealed lead acid because you can only discharge them up to 50%. A lithium iron phosphate, or the LiFePO, you'd be able to do up to 90% discharge. All of the details on the left is an example with two 12-volt 100 amp hour batteries, and just kind of giving you an idea. If you had 3 cameras, let's just say they run at 10 watts, that's 30, of course. If you have a wireless, about 4 watts. A switch, our switches that operate with these kits would need to be 12 or 24 volt input. They don't run very, they don't draw very much power. So just about 2 gives you about 36 watts, which is an amp and a half. So at an amp and a half consumption, you'd be able to get 33 1/3 hours of backup. And that means that you can run your equipment basing on the fact that there is absolutely zero sun coming in. But there will be some coming in. Even on a cloudy day, there will be some sun coming in. But this is based on maybe ice or something like that building on there that is completely blocking it, and you're not getting any power input. So on a 24 volt, 100 amp hour battery bank, you'd be able to do 33.3 hours. Now on the same bank, but lithium, you'd be able to do 60 hours of runtime. So that's the advantage there of a lithium battery, being able to do a whole lot more with the same type of equipment that's in the batteries. So if any questions now, I know we're up against it, but we've already done the product line overview. If you want to go through that again, we have that recorded and available on our website. We can take you through it as well. On that webinar, we talked about some other presentations like the one we just did just now, but there's also the secure WAN through-link discussion. There's mobile surveillance that we have too that we can talk about. So if you have more learning interest, let us know in the chat area there. If you have an application, then definitely let us know. We'll help you out with it.